The arrival of the interstellar object 3I Atlas into the inner solar system has captured the attention of astronomers worldwide. But what has drawn even more fascination in recent days is the detection of what appears to be a form of gyroscopic jet stabilization in its motion, something rarely, if ever, associated with comets. As NASA researchers, along with teams using various telescopes and observatories, continue examining this unusual visitor, an unexpected layer of complexity has begun to surface. Not only is the comet moving at extreme velocities on a hyperbolic path that unquestionably indicates origins beyond the solar system, but is also displaying jet-like outflows, remarkable rotational steadiness, and behavior that defies standard comet models. Before we begin, remember to hit the like and subscribe buttons for more updates. Since its discovery on July 1st, 2025, by the Atlas Asteroid Terrestrial Impact Last Alert System Observatory in Chile, 3I Atlas has been under persistent observation. Even the initial details were astonishing: an interstellar object, unbound by the sun's gravitational pull, racing through space at speeds exceeding 200 kilometers per hour. But beyond its trajectory and velocity, what now commands scientific intrigue are the physical processes occurring within and around it. Jets of material erupting from a nucleus and subtle signs that the nucleus behaves with rotational stability, almost as though acting like a spinning gyroscope in vacuum, are puzzling specialists. Typically, when sunlight heats the icy surface of a comet, sublimation causes gas and dust to erupt outward, a phenomenon well understood. Yet with 3I Atlas, this familiar process seems amplified, highly organized, and far more perplexing. Observations show a sharply directed jet shooting outward in a line that surprisingly angles toward the sun. An unusual sight, since comet ejecta generally flow away from sunlight due to radiation pressure and solar wind. Even more curious is that this jet's orientation appears stable, and the comet's rotation may be locking this jet into place, almost as if the nucleus and its immediate environment behave as a gyroscopic system maintaining steady angular momentum. This is where the idea of gyroscopic jet stabilization becomes relevant. If one imagines the nucleus and coma as a rotating structure, then a jet erupting from a fixed point should normally shift the comet's spin state. But if the jet remains firmly aligned and persistent, the only reasonable explanation is that the rotating body has reached a stabilized configuration, much like a top spinning fast enough to resist external torques. One research note proposes that if the coma becomes sufficiently ionized, interactions with magnetic fields and plasma could embed a stabilizing effect, helping the rotation resist disturbances such as solar wind or coronal mass ejections. Imaging shows the jet from 3I Atlas stretching perhaps tens of thousands of kilometers from the core. One estimate reaches around 10,000 km or more. But the size of the jet is not the main anomaly. What stands out is the precise, unwavering direction of the outflow, and the fact that its source remains tied to one region of the nucleus instead of shifting or fading, as is common in most comets. Typically, jets appear and disappear, drift across the surface, and change orientation as the nucleus spins or evolves. The stability here hints at a deeper internal feature or ongoing mechanism that keeps this jet aligned even while the object barrels through space at extreme speeds. Combined with its interstellar origin, this stability explains why scientists are buzzing with excitement. Since this object formed outside the solar system, its composition, radiation exposure history, and structural resilience differ drastically from comets born in our neighborhood. The jet and gyroscopic behavior may therefore offer insight not only into cometary physics, but into the behavior of long-travel bodies forged in completely different stellar environments. If the nucleus has managed to retain a coherent spin and structure after countless years drifting through interstellar space, that in itself is astonishing. Looking deeper, the jet seems to originate from a region that consistently faces the sun, suggesting solar heating is certainly involved. Yet its unchanging orientation implies that the rotation axis of the nucleus is somehow aligned with the jet's source. One possibility is that a specific surface or subsurface pocket of volatile ice or structural fissure is heated continuously as the comet approaches perihelion, and that this active region lies in alignment with the rotation axis, producing a steady, sun-facing jet, even for solar system comets. Such a configuration would be unusual. In the case of an interstellar wanderer, it becomes extraordinary. Gyroscopic behavior points to strong conservation of angular momentum in conditions where forces like radiation, solar wind, and outgassing should disrupt the motion significantly. The fact that 3I Atlas appears to maintain its jet direction and rotation axis suggests its angular momentum vector is highly stable. This leads to questions about its structure. Is the nucleus spherical or flattened? Does it contain internal support structures that enable steady rotation? Is the surrounding coma or plasma environment interacting with solar magnetic fields in a way that reinforces stability? Could ionization be generating magnetic effects that act like stabilizing flywheel? Such observations require stepping back to consider broader implications. First, if interstellar comets can preserve this level of structural and rotational integrity, our understanding of comet survival and long-term evolution may require revision. Most comets undergo cycles of erosion, fragmentation, rotation changes, and chaotic tumbling. Yet 3I Atlas seems to have preserved a strong spin and active jet mechanism despite possibly traveling for millions of years through deep space. This may mean that large, icy bodies from other star systems can endure far longer and store structural features that activate dramatically when they enter a new star's environment. Second, the presence of a stable, axis-aligned jet may allow researchers to treat the comet as a natural experiment for rotational physics. By measuring the angular momentum, estimating the forces from the jet, and tracking the resulting trajectory deviations, scientists may infer internal mass distribution, the moment of inertia, rotation period, and possibly even internal layering or voids. These clues help reveal whether such objects are solid blocks, loosely bound clumps, or structured bodies shaped by stresses during formation or ejection. Third, interstellar comets like 3I Atlas act as remote samples of distant star systems. Even though we cannot physically retrieve material from them, studying their coma chemistry, jet mechanics, rotation, and response to the sun gives us indirect information about the environments in which they formed. A persistent, stable jet may indicate internal channels or fissures shaped by heating cycles near their original star, allowing scientists to infer aspects of that star system's past. In this case, another important observation paired with the gyroscopic jet is the presence of non-gravitational acceleration at perihelion. The comet's path shows slight deviations from what gravity alone would predict, meaning the jet's thrust is altering its course. A stable jet implies a stable thrust vector, making the accumulated force measurable over time. Given the object's immense speed and hyperbolic escape trajectory, this creates an unprecedented opportunity to quantify outgassing forces on an interstellar visitor. These measurements could refine how we model the life cycles of such bodies as they encounter new stars. The persistence of a fixed jet also suggests internal durability, as the jet continues to erode the same region. The fact that this area retains its orientation means the nucleus must have considerable rigidity and mass. It does not deform or shift easily, resisting the chaotic behaviors many comets exhibit under solar heating. Solar system comets often experience rotation changes or even tumble unpredictably under strong outgassing. Yet 3I Atlas has remained remarkably consistent. This hints that interstellar comets may possess physical properties distinct from those born within our own system. If these objects arrive already spinning in stable configurations and maintain them through intense heating, then their ejection from their parent star systems might have left them with robust rotational states that survive across cosmic timescales. This also has consequences for future mission planning. If humanity ever attempts to intercept interstellar objects like 3I Atlas, knowing that jets may align predictably with a rotation axis would help engineers plan trajectories, sampling strategies, and hazard models, instead of viewing interstellar comets as unpredictable debris. Mission designers could treat them as active yet stable bodies with physics that can be anticipated. The extended stability of the jet also ensures that the same active region can be monitored repeatedly. a scientific advantage for long-duration observational campaigns. By observing the same jet region over an extended period, researchers can track variations in output, chemical makeup, temperature, and shape under a relatively constant viewing geometry. Experiments with such long-term geometric stability are extremely rare in small-body studies. This makes 3I Atlas a potential natural laboratory for examining how sustained jets develop, how they shift as the object moves farther from the Sun, and how its rotational stability responds to ongoing mass loss. The astrophysical backdrop is equally important. Interstellar comets like 3I Atlas are extraordinarily uncommon, this being only the third confirmed interstellar object. Detecting gyroscopic jet stabilization in one of these few cases marks a significant breakthrough, pushing the limits of our understanding. It challenges the outdated view of comets as simply chaotic, outgassing bodies, and instead points to a deeper, more intricate dynamic governing objects originating beyond our solar system. It prompts questions as well. Is this stability a unique trait of 3I Atlas? Or might upcoming interstellar visitors display similar behavior? Could the phenomenon relate to the comet's birthplace, its age, its composition, or the mechanism by which it was expelled from its original star system? Is it possible that certain interstellar comets are predisposed to activate stable jet structures when they approach a new star? From a compositional angle, evidence increasingly shows that 3I Atlas is far from ordinary. Measurements reveal elevated carbon dioxide relative to water in the coma, significant nickel content in its dust and gaseous emissions, an anti-tail configuration, and other indications of an unusual internal arrangement. The presence of jet stabilization alongside these factors suggests a relationship between internal material makeup, the longevity of active surface regions, and rotational behavior. A high CO2 fraction might enable sustained sublimation-driven jets with minimal disruption to surrounding ice layers. The nickel abundance might influence magnetic interaction within the ionized plasma surrounding the nucleus. The combination of the anti-tail and plasma behavior may help establish conditions favorable to gyroscopic steadiness. Whatever the exact mechanism, the correlation is worth deeper study. On a larger cosmological scale, the ability of an interstellar object to enter a stellar environment, maintain active jets, preserve rotational stability, and exhibit noticeable non-gravitational acceleration implies that such bodies may slowly reshape their trajectories in subtle but meaningful ways. This could influence the long-term behavior and distribution of interstellar wanderers. Perhaps their spin, shape, and path evolve as they encounter different star systems, altering how detectable they are and how they behave over time. If a jet can apply enough continuous force to create measurable trajectory changes, future detection and prediction systems may need to incorporate non-gravitational forces when estimating the paths and physical characteristics of incoming interstellar bodies. Observationally, the findings surrounding 3I Atlas highlight the value of coordinated, multi-platform, multi-wavelength campaigns. The jet was documented through ground-based facilities, including the 2-meter twin telescope at the TED Observatory, as well as space-based instruments, tracking the jet's orientation, imaging it clearly, and determining the rotation state of a nucleus all depended on well-synchronized efforts. Without high-resolution imagery, continuous monitoring, and trajectory modeling, the gyroscopic jet behavior might never have been recognized. This underscores the necessity of vigilant observation programs, especially those monitoring potential terrestrial impact systems like Atlas. One key takeaway is that the behavior of interstellar comets may not scale neatly from what we know about solar system comets. Our models of how jets ignite, how surface fractures distribute activity, how rotation couples with outgassing, and how nuclei withstand heating may require revision. The traditional framework of a spinning nucleus producing random bursts of activity may need to broaden to include fixed-axis jet behavior and gyroscopic stabilization involving plasma interactions and magnetic coupling. The fact that 3I Atlas displays such behavior hints that similar discoveries may await us, enriching the complex intersection of comet science, astrophysics, and plasma physics. Another compelling aspect involves the jet's interaction with solar wind and magnetic fields. A stable jet aligned with the rotation axis implies that expelled dust and gas continuously produce a plasma structure that interacts with the interplanetary magnetic field. If the nucleus spins, the escaping material might generate a spiraling sheaf or magnetically influenced pattern that helps maintain the jet's directional stability. In essence, the comet could behave like a self-organizing plasma gyroscope in which rotation, outflow, ionization, and magnetic forces collectively sustain a fixed orientation. While speculative, this concept opens new possibilities for understanding how small bodies may incorporate electromagnetic behavior into their motion. This is not merely theoretical interest. Grasping how jets, rotation, and stability interplay in objects like 3I Atlas enhances our ability to model their trajectories, anticipate mass loss, gauge structural endurance, and design missions, whether robotic probes or observational campaigns, to study or intercept such bodies for planetary defense. These considerations matter if an interstellar body were ever projected onto a threatening course. Although 3I Atlas will not come closer than about 1.8 astronomical units from Earth, the insights gained contribute to broader systems for monitoring both local and interstellar objects. The need to detect and confirm jet stability also emphasizes that astronomers must evaluate more than brightness or tail length. They must look for jet directionality, rotational patterns, and structural coherence. Some researchers have estimated a rotation period of roughly 16.16 hours plus or minus 0.01 for the nucleus of 3I Atlas, indicating a highly stable and quantifiable spin state. This measurement provides a basis for correlating the timing of jet emissions with the rotational cycle, allowing in-depth study of how the active region aligns with the spin axis and how outgassing torque influences rotation over time. In this sense, 3I Atlas is becoming a kind of Rosetta Stone for interpreting interstellar comet behavior, not because it reveals alien engineering or life, though speculative ideas have circulated, but because it compels scientists to revisit the physical principles governing small bodies. The concept of gyroscopic jet stabilization pushes research into a domain where rotation, plasma effects, and sublimation interact in unexpected, yet physically coherent ways. It encourages collaboration across astronomy, comet science, plasma physics, and aerospace engineering. In a broader philosophical sense, encountering an object from another star that still retains coherent rotation, jet activity, and structural stability serves as a reminder that consistent physical laws shape worlds throughout the galaxy. It demonstrates that the same forces sculpting objects in our solar system operate elsewhere, and that remnants from distant systems can enter ours carrying intact signatures of their past. It ties our solar neighborhood to the larger galaxy in a tangible, empirical way. With this in mind, attention now turns to observing the behavior of 3I Atlas as it moves farther from the Sun, how the jet diminishes or transforms, whether rotation shifts, and whether the gyroscopic effect persists. As solar heating decreases, sublimation will fade and outflow torque will lessen. Yet if the jet remains aligned even as its strength drops, that would be highly revealing. It would imply that once established, the jet axis remains fixed due to structural anchoring within the nucleus and underlying internal stability. For these reasons, the detection of a gyroscopically stabilized jet on 3I Atlas represents far more than a curious anomaly. It marks a significant moment in our expanding understanding of small bodies from beyond our solar system. It offers a view into the mechanics of interstellar visitors, the persistence of icy bodies, the interaction of rotation and outflow, and the plasma field behavior small bodies can display. It challenges, sharpens, and at times overturns our assumptions about comet behavior, urging the scientific community to refine its models and broaden observational strategies. The voyage of 3I Atlas will be continually tracked, scrutinized, and debated, yet the detection of stable jet activity marks a defining moment. It reminds us that the next interstellar guest will be examined not only for its orbit and makeup, but for its dynamic traits, spin, orientation, outflows, and any signs of hidden internal architecture. In that respect, 3I Atlas is both an alarm and an opportunity. It demonstrates that objects from the deep of space are not inert. random rocks but active entities that interact with a star's environment, preserve internal structure, and show persistent behaviors we can observe, simulate, and learn from. Future missions, telescope campaigns, and observation plans will reference this event as a case study. A comet that entered our system displayed a stable jet aligned with its spin axis, resisted external disturbance, and continued on its path. The gyroscopic character of its outflow hints at internal cohesion and rotational integrity and suggests new avenues of inquiry. We must observe, measure, and model to broaden our understanding of what comets, whether interstellar or solar system bound, can reveal about physical processes, formation, and evolution across the galaxy. The stabilizing jet on 3I Atlas continues to generate interpretations that extend well beyond the initial surprise at its discovery. Increasingly compelling is how this behavior ties into questions about the mechanical identity of interstellar objects, their evolutionary histories, and extreme physical regimes they endure while migrating through varied stellar neighborhoods. As more data accumulate, the comet shifts from astronomical curiosity to a dynamic exemplar showing how material from alien systems responds when exposed to the energetic conditions of a new star. Its jet, steady in direction and indicative of a deeply rooted internal mechanism, acts like a signature, evidence that the object carries more history, structure, and physical subtlety than a casual glance would imply. Focusing on the mechanics behind the steadiness enables deeper study of the forces involved. Solar heating as 3I Atlas entered the inner solar system triggered sublimation of volatile compounds in the nucleus. But that sublimation appears unusually coherent. Instead of chaotic eruptions producing transient plumes, the jet has become a persistent channel for material ejection. Such consistency implies a conduit or fissure that remains open, structurally reinforced or continually exposed, resisting collapse or diversion as mass escapes. In many solar system comets, channels shift or cease as seasonal heating changes or the nucleus rotates. Yet this interstellar body has preserved stability, hinting at some form of structural memory within the nucleus, geological or cryogenic architecture robust enough to survive its long interstellar journey and the current heating. The phenomenon prompts a rethinking of how interstellar comets might be physically and historically shaped. Unlike typical solar system comets, these bodies have likely endured numerous heating and cooling cycles during close passes by other stars or through regions of differing radiation. Their surfaces may carry scars from ancient encounters. Still, 3I Atlas behaves as if its active regions have persisted across vast time scales without major alteration. The jet's stability suggests interstellar comets might be more stratified, cohesive, or compacted by cosmic processes than previously modeled. Each observation of the object thus teaches us about how matter migrates, survives, and transforms over astronomical distances. Equally intriguing is how gyroscopic stabilization links with the object's trajectory. A steady jet direction produces a steady force, small but measurable. In the weeks around perihelion, trajectory measurements detected a subtle, persistent acceleration inconsistent with gravity alone, a non-gravitational effect attributable to the jet's thrust. What elevates the scenario is that the thrust vector stayed fixed for long intervals, offering a rare chance to treat the comet as a natural probe propelled by predictable continuous forces that can be modeled with precision. Trajectory analysts can use these observations to improve prediction methods for heating-activated incoming objects. Instead of coping with random outbursts, observers now face a case of mechanical regularity from an alien visitor. This has further implications for detecting interstellar origins. If some interstellar comets activate inherently stable jets, their paths may change more predictably than once thought, aiding efforts to backtrack their origins. Typically, tracing a parent system is extremely difficult because millions of years of gravitational interactions scramble trajectories. But a consistent non-gravitational force adds a traceable element, with long-term data characterizing that force. Researchers might one day link certain ejection regions or star clusters to bodies with specific spin, jet properties. Beyond origin questions, the jet's behavior informs ideas about volatile distribution in the nucleus. While many solar system comets have surface pockets that activate under heat, 3I Atlas seems to draw from a subsurface reservoir that feeds the jet steadily. That implies deeper internal structure, channels, layered ices, or veins, revealing clues about formation, gradual accretion in a distant protoplanetary disk, sculpting by collisions, or incomplete planet-building processes in its home system. A stable jet suggests either a reinforced channel or a self-sustaining material flow that prevents the vent from sealing. Balancing erosion and replenishment. A key interest area is how the comet's plasma environment couples to rotation. Material ejected by the jet becomes ionized by sunlight, forming a charged particle sheath. In most comets, plasma behavior fluctuates wildly with chaotic jetting, complicating modeling. Here, the jet's steadiness may produce a plasma sheath with persistent field alignments, rotational signatures propagating through the tail, and repeating magnetic coupling patterns each rotation. Those features offer unrivaled insight into plasma dynamics around small bodies, insights difficult to obtain even with close spacecraft encounters, which risk instrument damage in ion-rich regions. With 3I Atlas, astronomers have a remote but structured laboratory for studying long-duration plasma rotation coupling, improving understanding of how magnetic fields and plasma interactions buttress jet stability. If charged particles within the coma organize along field lines aligned with the rotation axis, they may help anchor the jet by creating electromagnetic scaffolding. Such a feedback loop, rotation maintaining jet direction, the jet producing plasma flow, the plasma aligning with magnetic fields, and that alignment reinforcing the jet could contribute to the endurance of orientation. In essence, 3I Atlas may illustrate how a small icy body can temporarily act as a complex plasma mechanical system. Moreover, its reasonably well-defined rotation period allows researchers to test whether the jet alters spin over time. If mass flow is strong enough, it can impart tiny torques and slowly change spin, effects seen in solar system comets, but often masked by unpredictable outgassing. The stable jet here permits controlled measurements, making small variations in rotation, acceleration, or wobble accessible to modeling. Comparing observed changes to predictions from rotational physics will test whether interstellar comets follow the same mechanical laws or whether their internal structures yield anomalies. Another interesting implication touches on astrobiology, not suggesting life aboard the comet, but considering material transport across the galaxy. Long-lived, stable jets imply internal conditions that preserve ices and dust over immense distances. If such bodies carry organic compounds, their internal robustness becomes relevant to theories of interstellar transfer of prebiotic material. A nucleus capable of maintaining internal order over millions of years could protect fragile molecules and deliver them to other stars intact. While 3I Atlas is not known to contain unusually complex molecules, the jet stability points to a durable internal composition and thus higher survivability for organics than often assumed for wandering icy bodies exposed to cosmic radiation. If you enjoyed this, please like the video and subscribe to the channel. Leave your thoughts in the comments. Will you make of 3I Atlas's gyroscopic jets and NASA's findings? We'd love to hear from you. Thank you for watching, and see you next time.